Hey, everybody, and welcome back to what will be our third episode in this AP review series. Our first two episodes centered on limits and then on continuity. And now we're going to move into the first really big part of calculus, and that's the derivative. And I thought about where to start with this review, and really I went back to how important it is to not only learn how to do these things, but understand the concepts and what they truly represent. The beauty of calculus and this branch of mathematics can't be stressed enough. So embrace it and focus on just fully understanding what the derivative is on a conceptual level so that you can use it and apply it to any situation where it would come up. And I want to actually begin this lesson with a quick graph. And maybe my graph starts like this and goes something like that. I don't know, it could be any picture. Maybe this graph represents something. Maybe this is our time axis in seconds, and maybe this represents distance in feet, right? And maybe this graph represents a runner's distance from the starting point at any given time as he goes through a race. So he starts at here's our starting line, and then his distance away over the first few seconds of this race. And I think if we're going to begin a lesson on the derivative, we need to start with the word slope. Because we should all know at this point that derivative and slope go hand in hand. And if we go back to probably Algebra 1, right, you probably learned that slope is the same thing, or could also be referred to as the average rate of change. So graphically, when we think about slope or average rate of change, we look at 2 points on the graph, and then we connect the secant line between those 2 points. And the slope, the rise over the run, that is the average rate of change over this interval. Maybe that's from time 1 to time 3 for our graph. What is his average rate of change over that interval? That could be what this represents right here. What is his average speed in feet per second, average velocity in feet per second over that time interval? Is a good number. But mathematicians really centered on, but what if I want to know what's happening at one point in time? If I want to know what is happening at time 1, not just over the interval from time 1 to time 3, what's happening at that point? This would no longer be a secant line, but as we all know, a derivative represents the slope of the tangent line at a point. So what is the slope? What is his rate of change at that point? So when we think of derivative, we're still thinking of slope, but now we're going to think of, instead of average rate of change, we're going to focus on instantaneous rate of change. So how fast is he going at that one moment in time? And you can imagine the power of this, the applications of this are huge. These are critical. So understanding that derivative as instantaneous rate of change, as the slope of the tangent line, are all crucial to your understanding of this part of calculus. So just making sure you know what it is, what it represents graphically, and then as we go through these next few episodes, how you deal with it algebraically, and then its applications to our real life scenarios as we go forward. Okay, so moving on a little bit, first bring up some different notations. So what are some different notations of the derivative? And some common ones that you could see, obviously we all know dy dx, our shorthand y prime. Maybe it's written as this. Lots and lots of different ways. F prime, can't leave off F prime, right guys? That's too important. Let's go back. Gotta have F prime, right? And think about the meaning of this. What is the change in y in terms of x? The derivative of our function y with respect to x. If I change this to dy dt, now this is in terms of t, which is probably going to represent time. It could be anything though. We could have dm dt. Maybe m represents the mass of something. This is our rate of change in that mass over time. Whatever it is. So lots of different notations. When you see these, you should think derivative, you should think slope, and everything that would come from those things. Second thing I want to talk about with the derivative is your formal definition. For you guys at this point in the course, I want you to be able to recognize the formal definition of the derivative. We don't have to go through the full limit problems that we've done, but you should be able to recognize the formal definition and then apply your derivative skills from there. But some different notations, and I'll kind of do the quick overview, but essentially the idea is the limit takes what would be a slope between 2 points and brings those 2 points together, right? We go back to our problem here. My red line, my average rate of change, we could think of this as change in y over change in x, right? Just like you did in Algebra 1, rise over run. So whenever we think of average rate of change or the slope of the secant, we're thinking of it this way. Now, if we look at this statement, the limit, putting this limit in the front, is going to bring the distance those 2 points are apart closer and closer together. So what's going to end up happening is it's going to be finding the slope of 2 points that are essentially right on top of each other. And if you go way back, beginning of the year, I presented the derivative in this way at first. I just want to kind of recall your knowledge today as you're reviewing. Some other takes on this, maybe it's the limit as x approaches a of f of x minus f of a over x minus a. Where a could represent just a, or it could be a point that you are finding it at. You might also remember, if I want to know, hey, what's the slope of the tangent line at a specific point? I can replace x with a, where a would then represent a number, maybe a slope at 1, a is 1, whatever it is. So these two here written at the top are the same definition, just a would stand for signify the slope at a point, whereas this would be a general notation of the derivative. And a problem that we've seen on exams from time to time. This is my example. Is if I give you a limit statement, maybe I say take the limit as h goes to 0 of the sine of x plus h minus the sine of x and all over h. And at first glance, this problem looks like a really confusing limit, but if we compare it to the formal definition of the derivative right here, we can see that this is a statement for the formal definition. And to find the function you're deriving, just look at right here, minus f of x. So we can see that this is saying to find the derivative of sine x. And as you're reviewing your rules, we should already all know, but just in case, that's cosine. So that's how I want you to be able to work with it in the next couple months as you're prepping for the AP exam, is recognizing formal definition of the derivative and then utilizing your derivative skills. Okay, one last piece today for this episode, and that deals with when does the derivative exist? Or maybe the better question to ask is, when does it not exist, right? If f prime of c, so if the derivative at c exists, we call this differentiability. So if a function is said to be differentiable at a point, that means that its derivative exists at that point. So the slope exists on the curve at that point. If we were to say that a function is differentiable over its entire domain, that means the derivative or the slope would exist at all points where that function is defined. So what we want to remember is, when does a function fail? Fail to be differentiable. And there are three cases, right? There's three times where this is going to happen that you need to know. The first would be at sharp points. Corners and cusps. Everybody likes the absolute value function. We can see that the absolute value function, the slope here is maybe -1. And then at this instant right here at the vertex, it changes to a +1. There would be a jump. If we were to graph the derivative, there would be a jump on the derivative graph at that point, so it fails to exist. Remember, it can also kind of go like this. If you have a piecewise look, any sharp point, the derivative, the slope fails to exist at that point. Option number 2 would be vertical tangents. And if we all agree that the derivative represents the slope of the tangent line at a point, and then you all agree that the vertical line has an undefined slope, the slope at that point would be undefined. And the last way would be any discontinuity. So if you think from last lesson, we looked at your jump discontinuities, your removable discontinuities, and your infinite discontinuities. Function's discontinuous, it can't have a slope at that point, so the derivative is going to be undefined. It's non-differentiable. So this kind of leads me into my closing statement today that I want to remind everybody of, is that let's say we know a function is differentiable. So differentiability implies continuity, which implies the limit exists. And this is an important statement. If a function is known to be differentiable, so it has a slope, then we can assume that it's also continuous, and then also the limit exists at that point, or at all the points if that's the case for the problem. But remember, the converse of this is not true. And remember, from geometry, converse means going the other direction. So if the limit exists, it's not necessarily continuous, and it's not necessarily differentiable. The only guarantee is this direction. It could go the other way, but not always. Whenever we think about must be true or could be true, it's important to know when things are true without a doubt. So differentiability implies continuity, implies the limit exists. Okay, that's it for today. Just a quick overview of the derivative. Hopefully this is helpful to you. Again, if there's anything else you'd like to see or anything else you'd like me to discuss with it, please let me know. And good luck with the rest of your studying and preparation. I'll see you guys next time.